Good afternoon, ladies and gentlemen. My name is Brandon White, and this afternoon my team and I will be discussing how do we engineer systems to manage data at exabyte scale. This is a very relevant problem in computer science today due to the exponentially increasing size of data sets in the last couple years. One of the biggest issues we will have to process in the future going forward is how to keep track of these vast amounts of data and actually make them useful to end users. To that end, there are a couple problems we need to deal with. The major hurdles to exascale data management are, first of all, the volume of the data, the veracity of the data, the velocity of the data coming in, and the variety and the value of the data. First of all, the data volume is huge, with 40 zettabytes or 43 trillion gigabytes total of data created worldwide by the year 2020, and numbers like 2.3 trillion gigabytes of data being created every day. It's very obvious that we will have to figure out some efficient way in which to manage these massive data sets in the future. Furthermore, coupled with the volume, is the data velocity, or rather, how fast that data is coming in. For instance, 1 terabyte of trade information is created during every trading session, which may contain billions of different transactions. Also, data variety will play a huge aspect. From text data to geospatial data to high-energy physics data to astronomical data to video data. The data in a modern data system will be varied, and we must ensure vigorous standardization of storage and communication protocols if we are going to guarantee that the system will operate smoothly. And finally, we have to ensure the veracity and the value of the data which our system is going to store. First of all, the veracity. If the system cannot provide correct data, nobody will ever use it. Nobody's going to use a system where they are provided with incorrect data. Furthermore, for the value, we want to make sure that the data is actually useful to the end user. We don't want to waste money by either storing redundant data or just storing plain useless data. So we went ahead and explored how Microsoft has been approaching this issue with their Azure Data Lake Store software. They describe Azure Data Lake Store as a hyperscale distributed file service for big data analytics, which is a fancy way of saying a really big file system. They said that they created it in order to have a modern data management system that could support huge scales of concurrent reads and writes, and also co-locate the data with the computation on that data in order to decrease the overall overhead of moving data around. Next, I will be followed by David, who will discuss how exascale datasets should be indexed.
In this section of the presentation, we'll be covering how data can be indexed in an exabyte scale system. First up is how should indexes be stored. In the Azure Data Lake paper, they compare themselves to the Azure Cosmos system. And so I chose to compare the two and to see how Azure Data Lake chose to improve upon the Azure Cosmos indexing system. In Azure Data Lake, indexes are stored as defined by the user. As you can see in the picture on the right side of the slide, there are currently 4 different options, those being range, hash, direct hash, and round robin. After looking at Azure Cosmos, I found that they defaulted different data types to 2 different distribution schemes, although this could be overridden by the user. In their case, Cosmos used a hash function to index string variables and a range index to index numeric values. Again, only by default, the user could override that. Personally, I felt that the Azure Data Lake implementation of this was an improvement over the Cosmos implementation. I thought this was the case because the Azure Data Lake system requires the user to be aware of the distribution scheme, whereas the Cosmos system left it way too easy for the unaware developer to forget to specify the scheme and it potentially default to a subpar distribution scheme. I then began to question what types of indexes were allowed in Azure Data Lake. Currently, they only allow for clustered indexes. They mentioned in some recent blog posts that their next priority is to extend their indexing to allow for column store indexes and secondary indexes. These types of indexes will allow for even greater efficiency in queries. I also saw that they would eventually like to continue expanding their indexing system to allow for non-clustered indexing, but it appeared that this was lower on their list of priorities. Each type of index could provide more benefit to certain structures of data more than it would for others, and so it's important to consider and to prioritize which types of indexes you want to implement. In Azure Data Lake's case, they chose that column store indexes were important, and this makes a lot of sense because column store indexes are very good at high levels of data compression. And so Azure Data Lake being a system that's meant for large quantities of data, it makes a lot of sense that column store indexes would be on their list of to-dos. Some examples as to how indexes are utilized in exabyte scale systems, I decided it might be prudent to take a closer look at how they were used in the Azure Data Lake system. As I said before, Azure Data Lake places the responsibility of creating the indexes on the developers rather than using some default distribution schemes. This is done after the user creates the table schema. As will be covered in more detail later, each file is broken down into partial files. Azure Data Lake maintains a table of these partial files, and it must index each partial file ID so that it can efficiently access them, as this is a crucial part of the Azure Data Lake system. Similarly, each partial file can contain many extents, whose IDs are also indexed as they are also used very often. In order to implement concurrency control, Azure Data Lake chose to index the last modified time on updated rows on their row insertion time value. This allows the system to quickly locate the most up-to-date value. The system must also be aware of how many entries are pointed to each ACL row in order to determine at deletion time if the ACL row can be deleted. In order to do this efficiently, Azure Data Lake chose to index the ACL ID, which they can then query and determine if there are 2 or more entries pointed to any given ACL row. I thought that it might be interesting to then look into how indexing could be improved further. The first thing that came to my mind was changing up how indexes are stored. Honestly, there wasn't much discussion in the paper or online about exactly what structures were used to store the indexes in the Azure Data Lake system, but I thought I would propose one that seemed to be a good fit. The issue that came to my mind was that everywhere I looked on the Azure Data Lake website, they were clearly very proud of their ability to handle petabyte-sized files. This made me wonder, though, what if you had an exabyte scale system, but instead of it storing petabyte-sized files, what if it stored a very large quantity of much smaller files? It seemed to me that, in this case, the size of the index would just explode. The sort of solution that I came to was a paper I found outlining the DCB tree. While I won't go into detail here, the main takeaway is that this structure was meant to store indexes in a very memory-efficient way. In the picture on the right side of the slide, you can see that when compared to other structures, the DCB tree was able to achieve a much more favorable outcome in terms of memory consumption. While the DCB tree may not be the final solution, I felt that it was important to note that in large-scale systems, it could be very beneficial to choose alternate structures to store indexes that require much less memory. In conclusion, I found that indexing in exascale systems was very similar to indexing in smaller systems. Indexes were similar in both the way they were stored as well as the way they were defined. The only difference I was really able to nail down was that in such large systems, indexing seemed to be even more vital to the success of the system, as it would otherwise just take a very long time to query anything. Next up, Nathan will cover how we can efficiently persist exascale datasets in the long term.
Another consideration for a system interacting with exabytes of data is how to efficiently persist the data. First question we can ask is if the relational model or the NoSQL model is better at persisting exascale data long term. I have narrowed down 4 key factors that we have learned about in this class, but we will look at them in terms of handling exascale data. As we have learned before, the relational model is best used with structured data, while NoSQL can handle structured, semi-structured, and unstructured data. As shown in this graph, as the amount of data has continued to increase significantly over the years, the majority of this data is unstructured or semi-structured, making NoSQL the better option in terms of the nature of the data. When considering the speed of interacting with exascale data, we need to weigh the cost of normalization versus the cost of storage. The complexity involved with normalizing exabytes of data in the relational model strongly affects the performance of data processing. NoSQL has data duplicated, like we've seen in the document structure, making it very quick to process, but with a higher storage cost. In the end, NoSQL has the ability to process the data quicker, which is often more important than the cost of storage. One of the major factors in handling exascale data is scalability. The relational model scales vertically, but when handling exascale data, there's a limit to how much a machine can handle on its own. NoSQL uses horizontal scalability, which is crucial for being able to handle more and more data efficiently, as more machines can be added as necessary when the amount of data increases. Finally, consistency is a factor to consider, where the relational model upholds ACID properties and the NoSQL model upholds base properties. In systems where ACID properties are extremely important, the relational model might be the best option. While NoSQL is eventually consistent, when dealing with exascale data, the other three factors that NoSQL outperforms the relational model will often be more important than the consistency. Therefore, eventual consistency can be tolerated in exascale systems. As you can see, NoSQL is better equipped to handle exascale data than the relational model. Within NoSQL, there are multiple different categories of databases, each with strengths and weaknesses with persisting exascale data. I'm going to cover a couple of the top options of NoSQL. An example of a key value store is Amazon Dynamo. The advantage key value stores have over other NoSQL database types is availability. With the amount of data constantly being added and queried in an exascale system, availability is an important factor to consider. HBase is a tabular store that is strongly consistent, unlike many NoSQL databases. This is a good option when consistency is important, but it comes at the cost of slower writes. Also, HBase is optimized for read performance, which improves querying large datasets. However, HBase is very complex, and large cluster configuration is known to be difficult as a result. Another type of database is document database, with an example being MongoDB. The advantage document databases have over the others is flexibility, as it is schemaless. However, with exabytes of data, this could end up being messier and more difficult depending on how complex the data ends up being. Finally, the advantage of graph database like Neo4j is that the structure can utilize index-free adjacency. This means all nodes directly reference adjacent nodes. This removes the need for indexes, making query processing speed independent of the size of the graph. That is very important when dealing with exabytes of data. The key aspect of how ADLS handles persisting exascale data is its flexibility. A secure store service provides an interface that storage providers can use to create a storage adapter. The secure storage service efficiently handles using different tiers of storage and different storage providers like Azure and Cosmos, which provides flexibility for the system. This flexibility is key for allowing the appropriate storage provider to be used based on the needs of the system. In the end, there is not a database that fits all systems needing to process exabytes of data. Different systems need to emphasize different factors. NoSQL is often better than relational when handling exascale data due to its superior handling of unstructured data and horizontal scalability. However, this comes with the cost of being eventually consistent. The type of NoSQL database that should be chosen based on which factors are more important for the system. Key value stores have the best availability, while document stores offer the most flexibility. Graph databases do not require indexes, which results in fast query processing, while HBase offers strong consistency. These factors should be taken into account when choosing a database that most effectively persists exascale data for the specific needs of a system.
Next, we will discuss how to support parallel and concurrent operations in Exascale data management systems and Azure Data Lake Store. So the real secret to this is making sure you partition your data horizontally in order for many concurrent readers and writers and processing processes to access the data without stepping on each other's toes. Microsoft achieved this at the file level in two separate ways. First, they divided their files into a series of extents, which is a sequence of each extent is a sequence of blocks that supports atomic operations and is each identified by a unique ID. What this allows is parallel execution of queries on a single file, where each part of the query can deal with its own extent and not worry about any of the others. They also went a step further and divided their files into partial files, which are a contiguous series of potentially overlapping extents. And what these allow is at the replication level for a file to be sharded over multiple storage mediums. This allows for different levels of redundancy per file and increases both the availability and the durability of the system. Microsoft also implemented a shared nothing architecture, quite reminiscent of Gamma, like we studied. They have a series of databases connected to a series of operator processes, with recovery processes and deadlock detection processes overseeing error recovery. But mainly, scheduler processes give jobs to the operator processes and handle the results and the delivery to the user in the end. The concurrency in Azure Data Lake Store, however, is handled by the naming service, which uses multi-version concurrency control to use snapshots to synchronize the file system operations, of which millions may occur every second. Reads are implemented at snapshot level isolation, where write operations use serializable isolation. However, this serializable isolation may be reduced in its stringentness so that more operations can be allowed to concurrently happen. This is implemented at the cost of code complexity, but allows for a greatly increased level of concurrent operation, provided that the data being operated on does not have to interact with each other. In conclusion, the easiest way to support parallelism and concurrency in these massive scale systems is to increase the granularity of the data structures and horizontally partition them for boosting throughput. And if you need to implement a multi-version concurrency control, if you don't need the absolute maximum level of isolation, reduce it. Next, we will talk about what must be considered for a file system at this scale.
What must be considered for a file system of this scale? This part of the presentation will try to include those those desired characteristics we hope to have in this file system at this scale. Data heterogeneity and elasticity is definitely one of the key characteristics we hope to have. How ADLS overcome this is they utilize Microsoft's internal file system called Cosmos, which marries Cosmos semantics with HDFS, supporting both Cosmos and Hadoop workloads. So now, apart from supporting unstructured data, it should also work with external data stores. So for that, they have HD Insight, which essentially is a wrapper over core Hadoop. So that way, the ADLS can work with the Hadoop and also with any third-party data stores. Next up, high scalability and availability is definitely a key requirement for a file system to succeed. Now, in the ADLS, there are a collection of core microservices, each of which need to be scalable, highly available, have low latency, strongly consistent. These core microservices are all built on a foundation. The authors call it RSL HK ring. All of these microservices, except for the throttling service, are themselves replicated systems. These take advantage of a replicated state library first that was built for Cosmos. These are deployed in a form-based ring, usually made up of 7 servers distributed across failure domains. Next up is ensuring low latency in the system. To overcome this, ADLS uses a small append service. So when small append service determine that a file's append part pattern is dominated by small appends, it cleverly switches them to small append path, which uses low latency storage to store the payload. Now, such appends are durable once acknowledged. Large appends are passed directly onto the downstream providers, and small appends are then collected asynchronously into larger append blocks before being moved to one of the storage tiers. As this figure that is taken directly from the paper, it shows the difference when SAS is enabled. You can clearly see from the numbers how fast it is. Next up is enforcing the strong consistency. It's a battle between having your system highly available and scalable, and then also be able to provide strong consistency. So how ADLS basically overcome this is ADLS builds on the core RSL approach discussed in the previous slide. It uses the SQL Server Hackathon engine. The combination of RSL and Hackathon leads to RSL HK ring. Now, this metadata service operations are written as a transaction with ACID semantic via Hackathon optimistic concurrency support. This way, service developers get fault tolerance for all state changes, including checkpointing, logging, and recovery. Next up is having robust data analytic capability. Obviously, storing massive data is pointless if the system doesn't provide efficient query analysis capability. To overcome this in ADLS, they have this thing called, within ADLA, Azure Data Lake Analytics. They have a combination of familiar SQL and C#. They call it GeoSQL. But basically, you put a path where the query is going to be run, and you also put your output path where the result is going to be written to. And not going too deeper into this, but it's kind of a combination of it combined together, as I said earlier, C# like semantics and SQL like semantics to provide you the query capability. Well, that said, that concludes the considerations for the file system. These are bulleted here. Obviously, we need these desired characteristic of heterogeneity and elasticity. Should be high scalability and availability should be there, low latency, strong consistency, data analytic capability. Obviously, there's always battle between trying to achieve one and losing another. For example, if you have high scalability and availability, you have to maybe give up some strong consistency to have eventual consistency. And that said, Next up, Brandon will conclude this presentation.
In conclusion, today we spoke of the different hurdles involved in Exascale data management, which is ensuring the different ways of dealing with the volume, the velocity, the variety, the veracity, and the value of the data. How to index Exascale datasets, which is very similar to normal indexing systems, but focused on efficiency. We discussed the persistence of Exascale datasets, where we found that NoSQL has an advantage over relational databases when you don't know what your data is going to look like. We also found that you really just need to pick one aspect of your system you would like to optimize. We also discussed how do we support parallel and concurrent operations in an Exascale data management system. The answer to that being expand your partitioning sideways to allow a greater number of concurrent reads and writes, and process transactions with the lowest level of isolation required to also facilitate that greater concurrency. And finally, we ended on how to support a file system of this scale, really stressing the fact that it must exhibit strong consistency so that the user experience is consistent, and high scalability and high availability are directly inverse to maintaining the consistency of the data. Thank you for your time today. The instructor will handle questions as we are all online students, and I hope you enjoyed this. Here are references. Does anybody have any questions? Thank you.